Magnetic circuits are employed to efficiently channel magnetic fields in devices such as transformers, generators, and motors. Hello everyone, my name is Rafael. I am an electrical engineer, and in this video I would like to invite you to observe the solution of 5 exercises concerning magnetic circuits that frequently appear in exams for electrical engineers. Let's go to the first exercise. Exercise number 1. Analyze the toroidal core and find an expression for the magnetic flux in which the mean radius is much greater than its width. Okay, my friends, this is the question. Let's go to the solution. The magnetic circuit of this toroidal core is analogous to a simple electrical circuit such as the magnetic circuit has a magnetomotive force, a flux, and a reluctance. This reluctance is the reluctance of the core, and the magnetomotive force is created by the passage of the current, and the flux flows in the core. It is analogous to the electrical current. Okay, we want to calculate the flux, but before calculating the flux, we need to calculate the reluctance. Let's calculate first the reluctance. The mean length of the magnetic flux path is going to be L equal to 2 pi r. Okay, this is the length of the path, okay, of flux. And the cross-sectional area of the toroidal core is circular, okay? It is a circle here. The toroidal core is circular. Then the cross-sectional area is going to be pi r squared. Therefore, we can use the expression of the reluctance. The expression of the reluctance is okay, the mean path length divided by the permeability of the core and the cross-sectional area. Using these values here, we find that the reluctance is equal to 2 pi capital R divided by nu pi r squared. And this gives a value of 2 times r divided by nu r squared. This is the reluctance of the toroidal core. Exercise number 2. Draw the electrical circuit analog for the magnetic circuit of the figure and determine the flux density in the core. This data was given by the exercise also. The exercise says that N1 is 500 turns, N2 is 200 turns, the cross section of the core is 3 centimeters by 3 centimeters, the path length is 36 centimeters, and the relative permeability of the iron core is 1000. This is the exercise. Let's go to the solution. Okay, if we pay attention to the way the coils are turned or wound around the core, we observe that they tend to cancel each other out. Let's use the right hand rule. Here, the current flows in this way. Then the flux is upwards. Here, the current flows in this way. Then the flux is to the right. Upwards here and to the right here, it means they subtract one another. They tend to cancel each other out. Therefore, the total magnetomotive is going to be the magnetomotive created by the passage of current in this coil here. I'm going to call it MMF1 minus the magnetomotive here. I'm going to call them MMF2. Okay? Let's calculate MMF1. It is going to be 500 turns times the amount of current, 2 amperes. And MMF2 is going to be 200 turns times 2 amperes. And this gives a value of 600 ampere turns. This is the total MMF. Okay, with this we will work on the magnetic circuit. The magnetic circuit is going to be and the flux flows in this way here. Okay, 1000 ampere turns created by this coil here, 400 ampere turns created by this coil here, and one minus the other gives the equivalent circuit as okay, this is the circuit representation of what we calculated. But lastly, we need to calculate the reluctance before finding what the exercise wanted us to find, which is the flux and the magnetic flux density. Okay, let's calculate the reluctance. The reluctance is going to be okay, the mean path length, the relative permeability times the permeability of free space, and the cross-sectional area of the core. If we use the values, we're gonna get that this L here is this 36 times 10 to the negative 2 meters. Okay, we are not going to use centimeters, we are going to use meters. The relative permeability is 1000. This is frequently a given, you do not need to memorize this. Frequently the exam gives you this value here, and it is 4 pi times 10 to the negative 7 Weber per ampere meter, and the cross-sectional area is 3 centimeters by 3 centimeters, which is 9 times 10 to the negative 4 meters squared, and we find a value of 318.3 times 10 cubed ampere turns per Weber. Alright, this is the reluctance. With this value of the reluctance and this value of the MMF, we can find the flux. The flux is therefore the division between this and this, and we find 1.85885 times 10 to the negative 3 Weber, and the magnetic flux density is the flux divided by area, which is, you simply divided this by the area, which is 9 times 10 to the negative 3 10 to the negative 4 meters squared, and this gives a value of 2.1 Tesla. Okay, my friends, this is how we calculate the flux and the flux density for a ferromagnetic core that can be used in a transformer, for example. This is all for exercise 2. Let's go to exercise 3. Exercise number 3, calculate the flux in each leg of the magnetic core of the figure. Okay, this is the exercise. It is going to be a simple one. We just need to use the theory that we have already seen, coupled with the theory of simple electrical circuits. N is given as 1000, the cross-sectional area is 2 centimeters by 2 centimeters, and the relative permeability of the core is 5000, okay? This magnetic circuit can be modeled as the magnetic force reluctance of leg 1 reluctance of leg 2 and the reluctance of leg 3. Okay, and here we're gonna call this flux here phi 1. We're gonna call this flux here phi 2, and then we're gonna call this flux here phi 3, and this is the MMF. Okay, Firstly, let's calculate the reluctance of here, here, and here of the first leg. The first reluctance is going to be, we're going to use this expression L over nu times A, and for the first leg, we're going to have 6 centimeters here, 6 centimeters here, 8 centimeters here, and 6 centimeters here, okay? So it is going to be 20 centimeters, which is 20 times 10 to the negative 2 meters, divided by the relative permeability of the core, which is 5,000 times the permeability of free space, which is 4 pi 10 to the negative 7 Webers per ampere meter, and combining the relative permeability of the relative permeability of free space, we get 6.283 times 10 to the negative 3 Weber per ampere meter, and the cross-sectional area, which is going to be 4 times 10 to the negative 4 meters squared. And carrying out this calculation, we get 79.58 times 10 to the negative 10 cubed ampere turns per Weber. Okay, this is the reluctance of leg 1. And if you observe, this is going to be also the reluctance of leg 3. Why? Because here is 6, here is 8, and here is 6, and there is no difference between leg 1 and leg 3. Okay, they are similar. Then the reluctance of leg 1 is equal to the reluctance of leg 3. Now we need to calculate only the reluctance of leg 2, which is going to be only 8 centimeters here, okay? Only 8 centimeters, which is 8 times 10 to the negative 2 meters divided by this permeability here, 6.283 times 10 to the negative 3 Weber per ampere meter, times the cross-sectional area that we already know, which is 4 times 10 to the negative 4 meters squared. And this gives a value of 31.83 times 10 cubed ampere turns per Weber. Okay? With these values, we can calculate the equivalent reluctance. The equivalent reluctance is going to be when we combine these two reluctances in parallel and we add this reluctance in series here. The equivalent reluctance is going to be reluctance number 1 plus the parallel connection between reluctance 2 and reluctance 3. Okay? is going to do the same as if they were simple resistances in an electrical circuit. You combine them in parallel. It is going to be the product divided by the sum. And to combine these resistances in series, you simply add the value, and we find a value of 102.3 times 10 cubed ampere turns per Weber. Alright, this is the equivalent reluctance. And why did we need to calculate the equivalent reluctance? We need to calculate the equivalent reluctance to calculate this flux here, phi 1, because we can see that phi 1 is equal to phi 2 plus phi 3. Okay? So, as phi 1 is equal to the sum of phi 2 and phi 3, to calculate phi 1, we need the total equivalent reluctance. Alright? And the circuit that we're looking for is going to therefore be, I'm going to erase it here. And the circuit that we are going to work on is this. This is the equivalent. And here, when I use the equivalent reluctance, the flux that flows here is phi 1, okay? Because we have combined all the reluctances, observing that phi 1 is equal to phi 2 plus phi 3. Alright, and then we discovered that phi 1 is equal to the MMF divided by the equivalent reluctance. Okay, using the values we just calculated, we're going to find that it is going to be 1,000 times 0.5, which is 500 ampere turns. 500 ampere turns, the magnetomotive force is 500 ampere turns. And dividing by the value of the equivalent reluctance, we get 4.88, 7 times 10 to the negative 3, Weber. Okay, this is phi 1. Now, we're going to use a technique used in electric circuits. I am going to, this is theoretical, okay? This doesn't exist, it is theoretical. I am going to use a MMF here, which I will call 2-3. 2-3, okay? This is from here to here. From here to here. Alright? What I'm doing is this. I am erasing all this, and I am using a theoretical value here. Okay, and here I'm calling to 3, and this is going to enable us calculate this. Okay. We know already that the equivalent in, reluctance between 2 and 3, okay, this is going to be the parallel connect between these two. It is 22.74 times 10 cubic ampere turns per Weber. And if we multiply, you're gonna see here, take a look at it, take a look at this, okay? All these models here will help us understand what we want. If phi 1 pass through the equivalent impedance here, and here flowing phi 1, what are we going to get? We're going to get exactly this. The magnetic force to 3, okay? And using this, we get that and I find the value of okay? If you understand electrical circuits, you're going to understand magnetic circuits because the way we work with them is similar. We use similar representations, okay? In electrical circuits, we would see that there is a voltage here and a voltage drop here, and there is going to be a voltage here, and we use this voltage here to calculate the current here and here. Alright, we are going to do the same to calculate the fluxes in magnetic circuits. There is an MMF here, and there is a MMF here, okay, that results from this one, okay. This does not exist without this. There needs to be this first for this to exist. And once we calculate this, we can find the fluxes here and here. This is exactly what we calculated. And to calculate this, the value of this, we firstly combined these reluctances here in parallel, and we found an equivalent reluctance. And when phi 1 passes through the equivalent reluctance, it produces this. And this is the value that we just calculated. And why do we need to use this? We need to use this because it is going to be applied here. And if we divide this value here, by the reluctance number 2, we get phi 2. And if we divide this value here by reluctance number 3, we find flux 3. Okay? So phi 2 is equal to okay, we divided this by reluctance number 2 we have already calculated. I related it here because I needed some space, but if you return the video, you're gonna see that there is a value for this, and we discovered that phi 2 is 3.49 times 10 to the negative 3 Weber, and the phi 3 can be calculated in the same way. And this is 1.396 times 10 to the negative 3 Weber. Alright, these are the fluxes. And exactly what the exercise wanted. The exercise wanted us to calculate the fluxes in each of the legs of this core. Firstly, we needed to calculate the reluctance of each leg. We calculated for this, and we discovered that leg 3 is equal to leg 1, then the reluctances are equal, and we calculated the reluctance in leg 2, and we use the magnetic circuit to calculate the flux. We use the equivalent reluctance to calculate flux 1, and we use this technique here that we learned when studying electrical circuits to calculate phi 2 and phi 3. Okay, my friends, this is all for exercise 3. Let's go to exercise 4. Exercise number 4. Consider the magnetic core with an air gap as shown in the figure. The core material has a relative permeability of 6,000 and a rectangular cross section 2 centimeters by 3 centimeters, and the coil has 500 turns. With this data, the time and the current required to establish a flux density of 0.25 Tesla in the air gap. Okay, my friends, this is the exercise. Let's go to the solution. We are going to observe the details of this figure to calculate what the exercise wanted us to calculate, which is a flux density. We want to calculate a current. The current I that sets a flux density of 0.25 at the air gap. Alright, let's model this circuit, this magnetic circuit, with an analogous circuit, analogous to an electrical circuit such as this. This is the reluctance of the core. The entire core, the reluctance of the entire core is modeled by this reluctance. And this is the reluctance of the air gap here. We are going to calculate this, but I'm going to tell you in advance that this is a very small gap, but its reluctance is much greater than the reluctance of the core. The exercises say that the relative permeability of the core is 6,000. Okay? So, the relative permeability of the core is 6,000 times that of free space of air, which means that the reluctance of the air gap is going to be much greater than the reluctance of the core. We are going to calculate it. And here, the MMF. Okay? And there will be a flux here. Okay? We are going to calculate all these parameters. The magnetic circuit is analogous to an electrical circuit with two resistances and 1 volt source. Okay? The MMF is analogous to a voltage source, and the reluctances are analogous to the resistances, and the magnetic flux is analogous to current. The reluctance of the core represents the reluctance. This represents the reluctance of the core, and this represents the reluctance of the air gap. Let's firstly compute the reluctance of the core. Notice that the center line, it is important because these values here, the reluctance of the core and the reluctance of the air gap, are not 100% precise, okay? It is going to be an estimate, and the estimate that we use while modeling electrical circuits and magnetic circuits is to consider the center line, okay? The flux will pass covering the entire path here, the interior of the magnetic core. However, if we compress these turns very tightly together, we can say that most of the flux will pass along the center line here. Okay? Along the center line. Not close to the borders, but most of them along the center line. And the center line, you see that the thickness here is 2 centimeters. If we take 1 centimeter here and 1 centimeter here, instead of 8, we're going to have 6 centimeters. Okay? Then notice that the center line of the flux path is a square. 6 centimeters by 6 centimeters. Okay? Instead of a square 8 centimeters by 8 centimeters is going to be 6 centimeters by 6 centimeters. Alright? Thus the mean length of the iron core is going to be the mean length of the iron core. Four times 6 centimeters, okay. We are taking 1 centimeter here, 1 centimeter here, 1 centimeter here, 1 centimeter here. Instead of computing for 8 centimeters, we are computing for 6 centimeters because we are considering that most of the flux will flow along the center, okay? Of course, this is not 100% precise, but this is the best estimate we can get without using a computer or any other kind of ultra advanced mathematics that requests a computer to help us. Minus the length of the air gap, which is 0.5 centimeters. And this gives a value of 23.6 0.5 centimeters. And the cross-sectional area of the core is okay, there is 2 centimeters in this direction and 3 centimeters in this direction here. 2 centimeters in this direction, 3 centimeters in this direction, and the cross-sectional area of the core is 6 times 10 to the negative 4 meters squared. Alright. And the permeability of the core is going to be the relative permeability times the permeability of free space, or permeability of air. And the exercises say that the relative permeability of the core is 6,000, and the permeability of air is 4 pi times 10 to the negative 7 Weber per ampere meter. Then the permeability of the core is going to be 7.54 times 10 to the negative 3 Weber per ampere meter. Okay, with this value we can calculate the reluctance of the core, and the reluctance of the core is going to be the mean path length divided by and the reluctance of the core is therefore 5.195 times 10 to the 4th ampere turns per Weber. Subsequently, we compute the reluctance of the air gap. However, to compute the reluctance of the air gap, we need to consider the phenomenon of fringing. Observe that the flux lines at the region of the core tend to bend outwards. Okay? Flux is channeled by the core. Okay? And as we have understood, most of the flux, provided that we compress and wind the coil very tightly together, the turns very tightly together, we have understood that most of the flux is going to flow deep in the core along the center line. And in this way, the core channels the flux. However, at the air gap, the core, the flux loses this medium through which it flows. And then it tends to bend outwards here in the core. This phenomenon is called fringing. And to deal with fringing, we need to use a technique. Okay? Of course, this is good for exams, but it is not good for transformer designers. They will need to use computers with algorithms to calculate these parameters, but for exams, for electrical engineers, this estimates that we are taking these approximations is enough. All right. An alternative to take into account the fringing effect is to add the length of the gap to the dimensions of the gap cross-sectional area. So the cross-sectional area of the gap is going to be, I have 2 centimeters here of this this length here, 2 centimeters, plus I'm gonna add the dimension of the air gap, 0.5 times, there is 3 in this direction here, okay? In exams for engineers, they actually accepted this, okay, this is right. It is not right for designing magnetic cores for transformers. You're gonna need to use another technique, more advanced. But for exams, it is enough and it is precise, okay? The number that we are going to find here will be regarded as correct in an exam. And this is all right. We're going to consider that the permeability of the gap is the permeability of free space, of air. And with this data, we can calculate the reluctance of the air gap. The reluctance of the air gap is going to be we simply use the value. This L gap here is 0.5 times 10 to the negative 2 meters. This is the permeability of air, which is 4 pi times 10 to the negative 7 Weber per ampere meter. And if we use this value here, we find that the reluctance of the gap is 4.5 times 10 to the 6th ampere turns per Weber. Okay? Observe that it's close to 100 times. The gap is very small, only 0.5 centimeters, but the reluctance of the air gap, it doesn't matter, okay? This is the core is much bigger than the gap, but the reluctance of the gap is 100 times, almost 100 times greater than the reluctance of the core. And this has a huge impact on the flux. Without the gap, the flux would be much higher, but with the reluctance of the gap, we have greatly diminished the flux. And the total reluctance is going to be, we simply add, we sum the reluctances and we find 4.6, approximately 4.6 times 10 to the 6th ampere turns per Weber. Okay, this is the reluctance of the total reluctance, the core and the air gap. We wish a flux density of 0.25 at the air gap. This is what we wish. We wish Bgap equal to 0.25. We simply use the number 0.25 here and the area of the gap, we calculated it, and we find the flux equal to 2.188 times 10 to the negative 4 Weber. And with this flux, the flux in the core is the same as in the gap. However, flux density is much higher in the core. Alright, now what we need to do is to use this value to calculate the current that is going to be able to set this flux density at the core. We're going to see that the MMF is equal to okay? We're going to use this value here, and we're going to use this value here, and we find a magnetomotive force of this magnitude, okay? And since we simply divide, it is going to be the division between the value of the MMF and the number of turns, which was given as 500, and we find therefore a current of 2.012 amperes. Okay? We need this current to have a flux density at the core equal to 0.25 Tesla. Okay, my friends, this is all for exercise 4. Let's go to the last, exercise 5. Exercise number 5. The iron core shown in the figure has a cross section of 2 centimeters by 2 centimeters and the relative permeability of 1,000. The coil has 500 turns and carries a current of 2 amperes. With this data, the exercise wants us to find the flux density in each air gap. Okay, my friends, this is the magnetic circuit, and this is the representation analogous to electrical circuits. Okay? Where RA is the reluctance of the left-hand path, the core and the air gap. RC is the reluctance of the center leg, and RB is the reluctance of the right hand path, combining the core and this air gap. Okay? Having understood this, we can move on to calculate the fluxes. We will need to calculate the fluxes phi A and phi B to compute the magnetic density at both air gaps. This is what the exercise wanted us to calculate. So to find the fluxes phi A and phi B, it is needed to firstly calculate the reluctances of the three paths. Okay? Let's concentrate firstly on reluctance RC. The reluctance RC is only the reluctance of this center leg here. And you can see that there is no air gap in this path here. Okay? So the reluctance RC is going to be only the reluctance of the iron core. Okay? This length here is 10 centimeters. 10 centimeters is 10 times 10 to the negative 2 meters. Okay? Instead of using 10 centimeters, we use 10 times 10 to the negative 2 meters. Now, the relative permeability of the core, it was given as 1,000. And the permittivity of permeability, the permeability of the air is 4 pi times 10 to the negative 7. Okay, it is a given. The exercise has to provide this information to you. It is not necessary to memorize it. And the area of the core, the cross-sectional area of the core, is 4 times 10 to the negative 4 meters squared. And if we use these values, we find that .99 times 10 to the fifth ampere turns per Weber. Now let's calculate the reluctance of the left-hand path and the reluctance of the right-hand path. Okay? For both the left and the right-hand paths, the total reluctance is the sum of the reluctance of the iron core with the reluctance of the gap. So, there is a portion of core here and the gap. So, the reluctance A of the left-hand path is going to be the reluctance of this portion of the iron core plus the reluctance of this air gap. We're calling it air gap A. Okay? And for the right-hand path, we compute in a similar way. Alright? The idea is similar for both of them, but there is a difference because the length of this air gap is different than the length of this air gap. Okay, the length of air gap A is greater than the length of air gap B. We take something else that we need to take into consideration is the effect of fringing. You can see here that flux lines bend outwards, okay, and they do not go straight here. And the permeability of air is different than the permeability of the core. So we have to compute this, we have to model this difference here. And how do we do this? We take fringing into account by adding the gap length to its width and depth in computing the area of the gap. So to take fringing into consideration, we need to add the measurements of the gap to its area. Okay, so the area of gap A is going to be 2 by 2, okay, but we have to add the measurements of the gap, okay. So instead of 2, it is going to be 3, because there is 2 centimeters in this direction, 2 centimeters in this direction, plus 1 centimeter of the gap here, okay? So it is going to be 3 centimeters by 3 centimeters, which is 9 times 10 to the negative 4 meters squared. And for air gap B, it is going to be 2.5 centimeters, 2.5 centimeters. Because here, the length is 1 centimeter, but here the length is 0.5 centimeters. Okay, with this data we can calculate. We need to calculate the reluctance. Thus, the total reluctance of the left-hand path is, the reluctance of the left-hand path is going to be okay, plus the reluctance of the core. Okay? And it is, if we use the values, we find 9.42 times 10 to the 6th ampere turns per Weber. Similarly, we find that for the right-hand path, using the values, we find that the reluctance of the right-hand path is okay. We have therefore calculated the reluctances, the reluctance of the center leg, the reluctance of the left-hand path, and the reluctance of the right-hand path. With these values, we are going to calculate the total reluctance. Okay? What we want to calculate the fluxes. But to calculate the fluxes, we're going to use a technique. We're going to have here if we combine these reluctances here, we are going to be able to calculate phi c, this flux there, okay? Understanding that phi c is equal to phi a plus phi b, alright? If you have understood this, we can understand therefore that R is equal to alright? There is a parallel connection between this and this, and to find this total reluctance, we simply add the reluctance of the center leg, alright? And thus we find that the total reluctance is equal to 4.2 times 10 to the 6th ampere turns per Weber. Alright? And now we can calculate phi c. The flux in the center leg can be found by dividing the magnetomotive force by the total reluctance. Okay? It's going to be this divided by, which is this, the magnetomotive force is 500 turns, okay, N times I. N times I. 500 turns times 2 amperes. Okay, simply use this value, 500 turns times 2 amperes, and we're going to use the value of the total reluctance, which is this. And we find therefore that phi c okay, this is phi c. And now, with the value of phi c, we can find phi a and phi b. Alright? We are going to use a technique, a current divider. I think you have already studied electrical circuits, and while studying electrical circuits, you have studied the current divider and the voltage divider. We use much more frequently the voltage divider, but if you remember the current divider, it is going to be very profitable to use here. So phi A is equal to phi C RB, RA plus RB, and if we use the values, we find that phi A is 101.1 microweber, and similarly we proceed for phi B, which is going to be equal to phi C and in this way, using the values, we find that it is 137 microweber. Alright, these are the fluxes. With this data, we can find the flux densities in the gap. The exercise wanted us to calculate the flux densities in each gap. Okay, This is gap A and this is gap B. And the magnetic flux density in this air gap is this is the flux that's going to flow in the gap, and this is the area of the gap. And we find alright. Similarly, we proceed for gap B. And the magnetic flux density in gap B is similarly calculated as phi B divided by AB, which is 137 microweber divided by 6.25 times 10 to the negative 4 meter squared, and this gives a value of 0.22. Okay, my friends, this is precisely what the exercise wanted us to calculate, and we have calculated the magnetic flux densities in each core. Okay, my friends, this is the video that I wanted to make covering the subject of magnetic circuits. I hope you enjoyed it and learned from it. I am a teacher. If you want to book a lesson with me, use my WhatsApp number, guys. Goodbye!